Welcome to Potty, May 07th, 2026. A deep dive.
Here's a question that should genuinely unsettle you. What if the most dangerous thing you did at work today was run git push? Not clicking a phishing link, not downloading a suspicious attachment. Just pushing code to GitHub, the way you do a dozen times a day without thinking. That's the core tension at the heart of CVE-2026-3854. A vulnerability that GitHub patched earlier this year, and one that I think deserves a lot more attention than it's gotten. Because the headline, GitHub RCE via git push, sounds almost too simple. Like, surely there's more to it than that, and there is. But the scary part is how much of the complexity is hidden inside GitHub's own infrastructure, invisible to the developer doing the push. Today, we're going deep on the full attack chain, the architecture, the injection primitive, the privilege escalation path, and what this tells us about the fundamental assumptions baked into modern microservice security. Let me start by setting up the architecture, because you really can't understand this vulnerability without understanding what's happening under the hood when you run git push. Most developers think of a git push as a direct conversation between their local machine and GitHub servers. You push, GitHub receives. Done. But that's not what's actually happening. GitHub's infrastructure has evolved enormously since its early monolithic Rails days, and today there's a whole translation layer sitting between your SSH connection and the core Git processing infrastructure. The key component here is called Babeld, and no, that's not a typo for Babel. It's a custom binary written in Go, and its job is to act as a protocol bridge. When you do a git push over SSH, Babeld picks up that connection and translates it into an internal HTTP request that then travels through GitHub's internal service mesh, so your SSH push never actually reaches the Git processing layer directly. It gets converted into HTTP first. And as part of that translation, Babeld and the surrounding Ruby-based processing code attach internal metadata headers to those HTTP requests, headers that downstream services trust completely. Now, here's where I want to pause and explain why that trust matters so much. Because this is the architectural assumption that makes everything else possible. In microservice architectures, and GitHub's infrastructure is absolutely a microservice architecture at this point. Services talk to each other constantly, and they use HTTP headers as a primary mechanism for passing authentication context, authorization decisions, and metadata. The implicit assumption is if a header says, "This request is from an authenticated admin user," or "This push has been validated," then it must be true, because only internal systems can set those headers. External traffic goes through a perimeter that strips or validates untrusted headers. Internal traffic is considered clean. This pattern is sometimes called implicit trust via header, and it's incredibly common. It's also, as CVE 2026-3854 demonstrates, catastrophically fragile the moment user-controlled data can leak into those trusted headers. A headline I came across from Wiz frames the CVE as a CVSS 8.7 vulnerability that enables remote code execution in GitHub Enterprise Server. And what I want you to hold on to is that 8.7 rating. That's not a theoretical bug. That's a drop everything and patch now rating. So let's talk about the specific header at the center of this, xstat. This is an internal header that GitHub's Ruby processing layer constructs to carry structured metadata about a push operation. The way it's built is by concatenating field values using semicolons as delimiters. So you might end up with something like xstat user Alice repo chew don't my project options equals deploy true. I'm simplifying the actual format, but the structure is key value pairs, separated by semicolons, all packed into one header value. Now, where do some of those values come from? They come from git push options. And here's what git push options are. For anyone not familiar, they were introduced in Git 2.10 back in 2016, and they let you pass arbitrary key value strings alongside a push using the O flag. So you might do git push O deployed to as production to signal to a CI/CD hook that this push should trigger a production deployment. They're legitimate, widely used, genuinely useful. GitOps workflows love them, and they are by design user-controlled strings that travel from the client all the way into server-side processing. Here's what most people get wrong about this vulnerability. They see the headline Git push RCE and assume it must be some exotic buffer overflow or memory corruption bug in Git itself. It's not. It's much more mundane, and in a way, much more embarrassing. The Ruby code that constructs the exstat header takes push option values and concatenates them into the header string using semicolons, but it never sanitizes or escapes those option values first. That's it. That's the root cause. So if I craft a push option that itself contains a semicolon, followed by something that looks like an additional header field, the concatenation logic just includes it. It doesn't know the difference between a legitimate delimiter it added and a malicious delimiter I injected. I saw one post on social media that tried to simplify this as just run git push o with a backtick command, and the researcher who found it correctly pushed back on that framing. There are more steps involved, but the core injection primitive really is that clean. You're breaking out of the intended exstat field and injecting entirely new header content into the downstream HTTP request. It's SQL injection logic applied to HTTP header construction. Same fundamental failure. User-controlled delimiters not escaped before being embedded in a structured, trusted format. Now let's follow the attack chain forward, because injection alone doesn't give you code execution. The question is, once you've injected a synthetic internal header into the request, what can you do with it? And the answer lies in pre-receive hooks. Pre-receive hooks are scripts that run on the server before a push is accepted. They're the mechanism GitHub and GitHub Enterprise Server use to enforce branch protection rules, run policy checks, trigger CI signals, that kind of thing. And critically, they run with elevated trust in the GitHub infrastructure context. They have to, because they need to make authoritative decisions about whether to accept or reject a push. So the attack path goes: inject a header that manipulates the hook execution environment, or leverage path traversal within the hook invocation logic to get arbitrary code executing in that elevated server-side context. GitHub's own post-incident write-up is titled something like Securing the Git Push Pipeline, responding to a critical remote code execution vulnerability, and the framing of securing the pipeline is telling. This isn't about a single broken function, it's about the entire trust model of the pipeline. Let me make the impact concrete, because remote code execution on GitHub can sound abstract. What does code execution in this context actually mean? You're running code inside GitHub's shared infrastructure, the same infrastructure that processes pushes for potentially millions of repositories. That execution context has access to things that are deeply, deeply sensitive. We're talking about the possibility of cross-tenant access to private repositories. Repositories belonging to organizations that have nothing to do with the attacker. We're talking about potential access to repository secrets, which is where most organizations store API keys, deployment credentials, cloud provider access tokens. We're talking about the ability to silently modify build artifacts or inject malicious code into CI/CD workflows before they deploy to production. There's a headline I came across framing this as GitHub fixing a flaw that gave access to millions of private repositories. And while I want to be careful here because that's being reported as a potential risk rather than a confirmed exploitation event, the architectural reality supports that concern. When your execution context sits inside a shared infrastructure layer, the blast radius is not scoped to your own repositories. It's scoped to the entire platform. There's another dimension to this that I think is underreported, and that's the GitHub Enterprise Server Security Mode bypass. GA, GitHub Enterprise Server is the self-hosted version that large enterprises run on their own infrastructure, and many of them have additional security controls enabled. Hardened configurations, additional authentication layers, enhanced audit logging, that kind of thing. The expectation from a security standpoint is that security mode means you have a higher baseline of protection. But what CVE-2026-3854 reveals is that those controls operate at a layer above the injection point. The header injection happens in the SSH-to-HTTP translation layer, in Babeld and the Ruby processing code, before the request even reaches the layer where those security controls apply. So you can have all your enterprise security bells and whistles enabled, and this attack still works, because it's bypassing the stack at a level those controls were never designed to address. My take is that this is a really important lesson about defense in depth. Controls that operate at the application layer don't protect you from vulnerabilities in the protocol translation layer underneath them. I want to spend a moment on GitHub's incident response here, because it's genuinely impressive and worth acknowledging. The GitHub security team validated, patched, and confirmed no exploitation in approximately 2 hours from the time of report. 2 hours! For a critical RCE in production infrastructure that affects potentially millions of repositories. There's a headline that frames it as how we validated, fixed, and investigated a critical vulnerability in under 2 hours and confirmed no exploitation. And if that framing holds up, that's a remarkable operational achievement. It suggests serious investment in incident response automation, automated detection pipelines, pre-built patch deployment infrastructure, forensic tooling that can rapidly sweep logs for exploitation indicators. Now, I don't want to be naive here. GitHub is a Microsoft subsidiary with enormous engineering resources, and this is exactly the kind of thing they should be able to do. But the 2-hour window is still notable as a benchmark. Most organizations, even large ones, would measure their critical patch response time in days or weeks, not hours. So, what does this vulnerability teach us about the broader security landscape? A headline I found from a developer-focused publication puts it well. CVE-2026-3854 is a useful reminder that security boundaries do not disappear just because traffic is internal. That framing is exactly right. And it points to something that I think is one of the most persistent and dangerous assumptions in modern software architecture. The internal traffic is safe. Assumption is everywhere. It's in how microservices authenticate to each other, how service meshes route traffic, how orchestration platforms like Kubernetes handle pod-to-pod communication. The Zero Trust networking movement has been chipping away at this assumption for years. The idea that you should verify every request regardless of whether it comes from inside or outside your perimeter. But Zero Trust is often implemented at the network layer, as mutual TLS, as service identity certificates. What CVE-2026-3854 illustrates is that Zero Trust principles need to extend all the way down to header validation, even on an internal network, even with MTLS between services. If one service constructs a trusted header by concatenating user-supplied data without sanitization, you have a vulnerability. Let me zoom out to the software supply chain angle, because this is where I think the stakes get truly alarming. GitHub is not just a place to store code. It is the upstream of an enormous fraction of the world's software build and deployment pipeline. Think about what sits downstream of a GitHub push. Automated build systems, container registries, package repositories, production deployment pipelines. When you compromise execution context inside GitHub's infrastructure, you're not just stealing data. You're potentially in a position to inject malicious code into software that gets shipped to millions of end users. This is the SolarWinds threat model applied to GitHub's own infrastructure. The attacker doesn't need to compromise individual organizations. They compromise the platform that all those organizations trust. A proof of concept demonstrating the XStat injection vector has been published, and multiple security researchers, including the team at Wiz, have done independent analysis of it. The fact that a working POC is public means that the knowledge of how to execute this attack is now widely available. The only protection is being on a patched version. And here is where I want to talk about the enterprise patch gap, because this is the part that keeps me up at night. GitHub.com. The cloud-hosted version was patched in approximately 2 hours. Great, but GitHub Enterprise Server is a different story. GS customers run their own instances on their own infrastructure, and they are responsible for applying updates. Enterprise software patch cycles are notoriously slow. Change control processes, regression testing requirements, scheduled maintenance windows, compliance review. All of these create friction that pushes patch timelines from days into weeks or months. There are organizations right now running unpatched GHS instances, not because they're negligent, but because their internal processes haven't caught up yet. And those organizations have a published proof of concept attack sitting out there, targeting a CVSS 8.7 RCE in their Git push pipeline. The researchers who found this and security news outlets covering it have been framing the risk to GHS customers in pretty stark terms, and I think that framing is appropriate. There's also a really important question that this vulnerability raises about the security review process for internal infrastructure code. When security teams do code review, they tend to focus their scrutiny on externally facing input handling, the API endpoints, the web forms, the places where untrusted user data enters the system. Internal header construction code, the kind of glue logic that builds metadata headers for internal service calls, often doesn't get that same level of attention. It's not glamorous, it's not the obvious attack surface. And yet, as CVE-2026-3854 shows, it can be the most critical code in the entire system. The fact that the xstat header was being constructed by concatenating user-supplied push option values without escaping them suggests that this code was probably written as utility infrastructure, not as a security-critical function. That's a categorization failure. Any code that embeds user-controlled data into a trusted internal channel is security-critical, full stop, regardless of how far downstream it sits from the user-facing layer. I want to draw a direct analogy here, because I think it makes the root cause viscerally clear. HTTP header injection of this type is, at its core, the same class of failure as SQL injection. In SQL injection, you have a database query being constructed by concatenating user-supplied strings, and the user injects SQL syntax that breaks out of the intended string value and becomes part of the query structure. Here, you have an HTTP header being constructed by concatenating user-supplied push option values, and the user injects header syntax, specifically semicolons and header name-like strings, that breaks out of the intended header value and becomes additional header structure. The fix in both cases is the same conceptually. Escape or sanitize user-supplied data before embedding it in a structured, trusted format. Parameterized queries for SQL. Proper encoding or stripping of delimiter characters for header construction. These are not exotic mitigations. They are foundational secure coding practices that have been in the curriculum for 2 decades. The fact that a vulnerability of this type existed in GitHub's infrastructure in 2026 is, my take, a sign of how easily internal infrastructure code escapes the scrutiny that we apply to external-facing code. Now, let's talk about what other platforms and systems might have analogous vulnerabilities, because I think this is genuinely the most important forward-looking question here. Babeld is GitHub-specific. It's their custom SSH-to-HTTP bridge, but the design pattern it embodies is not GitHub-specific at all. Any large-scale Git hosting platform that has evolved from a monolithic architecture toward a microservice architecture has probably built similar protocol translation layers. ITEA, Forgeo, Bitbucket Data Center, GitLab. They all have SSH-to-HTTP translation components. They all have internal header construction logic. And they all operate with some version of the internal headers are trusted assumption. The specific xstat header and semicolon delimiter might be unique to GitHub, but the underlying pattern, SSH push triggers translation layer. Translation layer embeds push option values into internal metadata. Internal metadata is trusted by downstream services. That pattern is generic. And now that CVE-2026-3854 has published a proof of concept and attracted serious researcher attention, I would expect systematic audits of those other platforms to follow. This CVE is going to serve as a template. Alright, let me shift into forward-looking analysis. And I want to be explicit that this is pattern matching from the research, not first principles prediction. But based on what we're seeing, a published PUC, a well-understood injection primitive, a CVSS 8.7 rating, and the historically slow patch cadence of on-premises enterprise software. One plausible trajectory is a wave of exploitation attempts against unpatched GitHub enterprise server instances over the next 6 to 12 months. I'm drawing a parallel here to GitLab CVE-2026-3854, which was a critical RCE in GitLab's image processing pipeline. That vulnerability was patched in April 2021, but exploitation attempts against unpatched instances were still being reported well into late 2021 and 2021. The gap between when the cloud-hosted version is patched and when the last enterprise customer applies the update is a structural vulnerability window. Threat actors know this pattern. They've exploited. And regulated industries, financial services, healthcare, government, are exactly the organizations most likely to have slow change control processes, and most likely to be running sensitive repositories that make them attractive targets. Here's the contrarian take that I think most people haven't considered yet. The real long-term impact of CVE-2026-3854 might not be the exploitation of unpatched instances. It might be what it does to the threat model for internal header construction across the entire industry. Before this CVE, header injection in internal service communication was a known vulnerability class in security textbooks, but it wasn't a concrete high-profile, publicly exploited case study that you could point to in an architecture review and say, this is what happens. Now it is. Security architects doing threat modeling for microservice systems are going to start asking, do any of our internal services construct headers by concatenating user-supplied data? And the answer in a lot of organizations is going to be yes. So, in a strange way, CVE-2026-3854 might end up being one of those vulnerabilities that catalyzes a genuine security improvement across a broad class of systems. Not because of the exploitation, but because of the clarity it provides about a previously underappreciated attack surface. If you're in a security architecture role right now, this is the case study you should be putting in front of your engineering leadership. There's one more implication I want to flag before we wrap up, and it connects to the Git push options attack surface specifically. Git push options were introduced in Git 2.10 back in 2016. And their adoption has grown significantly with the rise of GitOps workflows over the last several years. GitOps is the practice of using Git as the source of truth for infrastructure and deployment configuration. You push to Git, and automated systems pick up that push and deploy whatever it describes. This has made Git push options increasingly important as a signaling mechanism. You push code and include options that tell the CI/CD pipeline what environment to target, what approval gates to skip, what deployment strategy to use. That's a lot of semantic power embedded in a user-controlled string that travels through the push pipeline. CVE 2026-3854 should prompt every platform that processes push options to audit how those option values are handled at every point in the processing chain, not just at the point where they're first received, but at every subsequent step where they're embedded, logged, forwarded, or concatenated into other data structures. The attack surface for push option injection is probably broader than anyone has fully mapped. So let me bring this all together. When we started, I asked you to consider what it would mean if the most dangerous thing you did today was run git push. Here's what you now understand that you didn't at the start. The danger wasn't in Git itself. It wasn't in the push. It was in the invisible translation layer between your SSH connection and GitHub's internal services, a layer you never see, never think about, and have no control over. CVE 2026-3854 is a story about how complexity creates attack surface in places that nobody is looking. Babeld translates your SSH push into HTTP. Ruby code builds a metadata header by concatenating your push options. Downstream services trust that header implicitly. Nobody escaping the delimiter. That's the entire chain. Simple pieces, catastrophic combination. GitHub patched it fast, and to their credit, confirmed no exploitation. But the unpatched enterprise instances are still out there. The PUC is public, and the underlying architectural pattern exists in systems well beyond GitHub. If you're running GitHub Enterprise Server, check your version today. If you're building microservices, audit your internal header construction code. And if you want to go deeper, the Wiz blog breakdown and GitHub's own incident response write-up are both worth reading in full. They're unusually transparent about the mechanism and the response. The uncomfortable truth that CVE 2026-3854 leaves us with is this. We've spent years building sophisticated perimeter defenses, zero-trust network architectures, and advanced threat detection systems. And a developer with push access and a semicolon in the right place could have walked past all of it. The most dangerous vulnerabilities are rarely the exotic ones. They're the ones hiding in the boring infrastructure code that nobody thinks to audit, doing exactly what it was designed to do. Just a little too trustingly. That's the pattern to watch for. That's the lesson to carry forward. And the fact that this was found and patched responsibly is good news. But the fact that it existed at all should make every engineering team ask hard questions about what their own boring infrastructure code is trusting without verifying.